Hello. This is the final bit of work we're going to do on quadratics in the AS pure maths part of the course. And we're finishing off on this topic called modeling with quadratics. So we're not actually going to look at anything new per se, but we're going to start to introduce this idea of modeling with maths, right? Modeling there. And what modeling is essentially putting maths into real life. So these are questions based on real life scenarios. Um, and I guess modeling, you maybe think like computer modeling. So how we can simplify or make or put a situation into a computer, and the computer does some algorithms or some stuff to kind of solve the problem, right? So we have a real life problem, and then we simplify it and put it into a computer, and then the computer chucks an answer out, which we then can use to solve the real life problem. That is essentially that's the same sort of principle with maths, right? Mathematical modeling. We have a real life problem. We try to simplify that, convert it into maths, or convert it into a mathematical equation, which we can do something with. We can maybe solve it, and then we get a real life and then we get an answer from that, and then that answer will solve the problem that we have in real life. So it's actually quite useful, right? And this is why maths is useful, right? So, it allows us to convert a real life problem into maths. We can then use our math knowledge to solve that maths problem, which in turn then solves the real life problem. Okay, and so we're going to first look at this with quadratics because it turns out there are some examples, particularly as an example, if we were to throw some sort of ball in the air, if you were to throw it, say, like a baseball or something like that, it its motion forms this sort of arc, this parabola, right? Remember, parabola is basically the shape of quadratic. So remember, our quadratics either look like this or this, right? If it's a smiley shape for a positive quadratic, or a or frowny shape, if it's a negative. And in this case, the ball, when it goes up and moves, and then it reaches the ground back here, it forms a sort of quadratic shape, right? Which specifically, this sort of frowny shape here. And what that means is essentially, can we work out a quadratic equation for this path, this arc, this shape, and then we can work with use our knowledge of quadratics, so we can solve an equation or complete the square to perhaps find the maximum minimum, and so therefore then that allows us to tell us when the ball would reach the ground next by finding by considering the x-axis when it crosses the x-axis. So if this was the x-axis, for example, the roots will tell us when the ball hits the ground. And we can also find perhaps where the maximum would be by because remember, this would be a turning point, and that would be by completing the square. So we can find a sort of quadratic equation for this shape. We can work out quite a bit of information about it using our math knowledge, and that'll tell us, some real life information about the ball. So when it hits the ground, the maximum height it reaches, and so on. Okay, so that's just the introduction to modelling. Let's have a look at some questions then, because I think it's a lot easier to practice with questions. And we have this example here. So it's told us a spear is thrown over level ground from the top of a tower. The height in meters of the spear above the ground after t seconds is modelled by the function this here, and they give us this quadratic. Okay, so part A, interpret the meaning of the constant term 12.25. Okay, so the best thing, first of all, is actually consider what this function looks like. And last time we looked at sketching, right, the graphs of a quadratic. And in general, if we have minus 4.9t, it's a negative, so it's going to be like a frowny shape. And again, because it's thrown a spear, again, we're throwing something in the air, so it's going to, as we discussed earlier, is going to form this sort of frowny shape. But anyway, that's what the quadratic would look like. It's something like this, right? Because it's negative. But that just helps us visualize, what we're kind of working with. Okay. And so let's guess if we'd best draw an axis. Let's kind of get a more accurate representation of what the graph would look like. So we have minus 4.9t. So again, that's going to tell us the quadratic will have that shape. But very quickly, I can work out where the y-axis crosses. So where it crosses the y-axis, right? What's that going to be? Well, the y-axis is going to be when x is 0, right? Well, actually, no. In this case, we have variables h and t. So t and then h is the y-axis because we have t, which is our variable, and h, which is sort of like the y value, so what the function is. Anyway, so that's h and t, but it works the exact same way as x and y. But to work out then the where it crosses the h axis, right? That's going to be when t is 0, isn't it? So when t is 0, when it crosses the h axis, it's going to be this number here, 12.25. So if it has this sort of shape, it's going to probably look something like that, right? I don't know roughly where the mint maximum is. I don't know where the turning point is exactly. I don't know where uh, the roots are. I'm just saying that's roughly where it may be. Okay, so that's sort of what we're looking for. So that's kind of what the uh, sort of the path would look like. But actually, it's also said when t is greater than or equal to 0. So we only want positive values of t. So we only want this side of the graph, like not the left side. So where we're from. So actually, it would look something like this. So it crosses 12.25, and that's T and H. But I've got rid of the negative T axis, right? So I really want the right side of the graph. And that's a very common sort of thing, right? Normally, with these modeling real life problems, it would be T in terms of something else. So here it's H, but T would be time. So it has to be positive, right? Because you can't have negative time. So that's sort of the situation we're looking for, and so that's kind of what the motion of the spear will look like. Okay, so then it says interpret the meaning of the constant term 12.25. So interpret what that means is the key word you're going to see when we do these modeling questions. That means give what does this number, this term represent in the context of the real life problem, right? So here, a spear is being thrown from the top of the tower. So we need to work out what this number means in relation to this sort of scenario here of the spear being thrown from the tower. Well, again, 12.25, we already sort of discussed this. It's the sort of the h-intercept, right, where it crosses the h-axis when t is 0. Well, that's going to be a key. That's going to be a key idea. Is when t is 0, um, h is 12.25, right? Now h is height, and that's meters, and specifically, it says height of the spear above the ground after t seconds. Well, t is 0, so t is 0. That's the very start of the situation, right? The spear's not been thrown at the start, right? It's t 0. If you imagine it's a man or someone standing, it'd be on top of the tower, right? Someone is standing on top of the tower, then they've thrown a spear. So that's hit exactly when at the start when t is equal to 0, they're still at the top of the tower. So the spear would not have moved anywhere yet. It wouldn't have started its journey in the air. So initially the height is 12.25. Well, that's going to just be the height of the tower, isn't it? Above the ground. So imagine the ground is h is 0, which would be the down here, right? So h is 0, kind of like the t-axis, right? So if we got a height of 12.25, well, that has to be the tower because it's starting from the tower. So actually then interpreting it, see how I've given what that means in terms of the real life. 12.25 is the height of the top of the tower in meters, right? And that's really it. And so yeah, there we are, 12.25. So hopefully it made sense. So interpret again. Hopefully you see that I've explained what that means in terms of the problem. So I didn't just say 12.25 is the height when t is 0. I said specifically 12.25 is the height of the top of the tower. Okay. Which means I'm relating it to the problem with the real life problem we've got here. So we're talking about being from top of a tower. That's where I got that from. Okay, and often with these problems, we will look at more of these. This is a very prevalent topic of modelling, and we do it in a lot of different topics later on. You'll see more questions, but a general strategy with these sort of interpret questions when they give you some term here and says what is the meaning of this number? What's the meaning of this term? Usually it's the starting value. So here it was when t is 0, so the start of the model, right? So the start of when the equation happens, the start of when something happens. Usually that's what you want to consider. In this case, it was true because t is 0 gives a height of 12.25. So that's the starting height. Well, that'd be the height from the top of the tower. Anyway, so that's part A. Part B then says, after how many seconds does the sphere hit the ground? So when it hits the ground, then well, we already discussed this already in a way. So the ground is this sort of h is 0, right? The t-axis. So in other words, when the sphere hits the ground, it's going to be it's going to be when it crosses the x of the t-axis, right? And when it crosses this, well, how do we get this? Well, that's when h is 0, isn't it? But when h is 0, the whole quadratic equals 0, doesn't it? So minus 4.9t squared add 14.7t add 12.25 equals 0. Well, that's an equation we can solve, isn't it? So we could just solve that by quadratic formula. So t would be minus 14.7, and that is a t there. Minus 14.7 plus or minus the square root of 14.7 squared minus 4 lots of minus 4.9, 12.25 over 2a. Well, that'd be 2 times minus 4.9. Oh, oh dear. So put that in the calculator or put that into your solver thingy. Do, 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 you should get these two values. So t is 3 plus or minus root 19 over 2. And so if we put that to decimal, so t would be, so if we do the positive case, so 3 plus root 19, you'd get 3.68 to 2 decimal places, I'm doing it, or t is equal to minus 0.68 to 2 dp. Okay, but we've got two values. So this is so, but remember again back to the question: t is time. So, and specifically, it also says t has to be greater than 0, well, greater than or equal to. It has to be non-negative, right? It cannot be negative. So really, we must only take the positive answer, right? So t is greater than or equal to 0, so t cannot be negative. So t is 3.68. And that's our only solution. And usually, again, that's what you kind of want to do in these sort of questions. You might get multiple answers, but you're going to need to rule one of them out. And usually, it's because cannot be time cannot be negative, so therefore we have to reject this solution and only accept this one. So that's our solution, which makes sense for our graph again, doesn't it? Because if we were to, if we look back to the graph we sketched here, we had when it crosses the t-axis on the negative, and when it crosses the t-axis on the positive. So it makes sense we get negative and a positive, but in this case, we only have the positive answer. So that's our answer. So t is 3.68, and t is specifically in seconds, so that'd be 3.68 seconds. Cool. Um, okay, then part C says write h of t in this form here. Hopefully you recognise this is incomplete. This is completed square form because we have a bracket of t, sum lots of t, it's all squared. So it's complete in square. Okay, so let's copy our function. So it says h of t is equal to minus 4.9t squared at 14.7t, add 12.25. So we need to complete the square in this. So first of all, again, we looked at how to complete the square earlier in the chapter. So what you're going to do first is factor out this minus 4.9 to just get t squared. Then I need to do the same for here. So I need to factor out minus 4.9. So how to work out this number here, I'm going to put here for t. I can just do 14.7 divided by minus 4.9. And actually you get negative 3. So there we are. So if you get if you get nasty numbers like this and you need to factorize or pull something out, you can just divide it. Okay, so 14.7 divided by 4.9 tells us what number we need to put in. And there. Anyway, so that's t squared minus 3t. Then we add this 12.25 at the end. Then we can complete the square inside here. So that would be minus 4.9 t, then t minus a half of that, so 3 over 2 all squared. Then I'm going to minus the square of that, so it's 9 over 4 plus 12.25. Then if I expand it, I'm going to get minus 4.9 of t minus 3 over 2 all squared. Then I'm going to do minus 4.9 times by minus 9 over 4, and you get 11 point, plus 11.025 plus 12.25. Then you get this minus 4.9 over t minus 3 over 2 all squared. Then I could just add these two numbers together. So then I get 23.275. Cool. Okay, so that's written in that form. Cool. Then part D. Using your answer to part C or otherwise, find the maximum height of the spear above the ground and the time which this height is reached. Well, again, the maximum, well, that's going to be this turning point, this highest point here. But we know how to use the complete score. We looked at it last time when we looked at graph sketching. So the maximum point corresponds to when we have the completed square form. And again, it said hence use part C. So we need to use part C to work out this answer. Well, we complete the square already. So to work out I'm going to do part 2 here. The max height, well, that's going to be when, the maximum height, that occurs when the bracket equals 0. So for that to happen, t has to equal 3 over 2. Which is obviously at 1.5 seconds. And then the maximum height is, well, if this bracket equals 0, well, then this whole thing goes away. So that'll all go to 0. So I'm just simply left with the number outside. So the maximum height, so remember h would equal this whole thing, because h of t is equal to that. So h, then, we're left with 23.275. So that will be 23.275 meters for the maximum, and therefore the time is when again the bracket equals 0, so I have to set t to equal 3 over 2, and that'd be 1.5 seconds. Cool. That's it then. Nice. So as you see there, I've not actually done anything new, anything different. I just solved an equation. I know how to do that. I've done that in the first section when we looked at solving quadratic equations. Then we completed the square, and then we used that to find the maximum. Nothing new there. We looked at that when we did graph sketching. Nothing new there, but as you can see, there's a real life problem involved now. But as you can see here, this goes back to what I was on about with modeling, is that we have a real life problem or real life scenario, then we convert it into maths or convert it into a mathematical equation. Then we solve the maths, right? We'll solve the maths equation. So here, what we did here is, well, they did the first bit for us. We have a real life problem, and then they gave us the quadratic, right? So they told us the projection. So the motion, the movement of the sphere looks like resembles this quadratic, which we see here, right? This graph here. Um, so it resembles that, and they told us the maths equation. Then we solved it. We worked with the maths, so we solved the quadratic equation to find when it hits the ground, which we did in part B. We also completed the square to find the maximum height it reaches. So we did some maths there. So we solved the maths. Therefore, we have a solution to the problem, right? So, in other words, for example, part B, say the archer, whoever threw the spear, wanted to know how long until the spear hits the ground, but therefore then we have to sort of model it. We have to make a mathematical equation. So we notice the spear looks like it's moving in a quadratic fashion. So we found a quadratic equation. Then we could complete the square, which enabled us to find the maximum height. And therefore, there we are. We got not the maximum height, but also to solve the equation then to get when it hits the ground, right? So we set the whole thing equal to 0, and that allows us to tell us when it hits the ground. And so that's essentially the recipe for mathematical modelling. So we get real life problem again, convert it into maths, or most likely it will basically means find an equation to represent what's going on. So here the quadratic equation tells us the motion of the sphere. Then we can solve the maths or do something with it, and then once we solved it, well, therefore that's the solution to the problem. Okay, cool. Now we're gonna look at some exercises, but in particular, I want to look at a bunch of exam questions instead of just looking at a textbook because I think that's way more useful. Okay, and they do ask this quite a lot as well. So it is quite important. You do sort of get an idea for what's going on here. Okay, so it tells us that in this question, a roller coaster ride. On a roller coaster ride, passengers travel in carriages and a track around a track. On the ride, carriages complete multiple circuits such that the maximum vertical height of the carriage above the ground is 60 meters. The carriage starts a circuit at the vertical height of 2 meters above the ground. The ground is horizontal. The vertical height h of a carriage above the ground, t seconds after the carriage. The first circuit is modelable the equation. So what they do not just throw a lot of words in. That's just unfortunate. That's real life for you. But really the strategy is to just highlight the main things. So I always highlight the units. So the variable, so h in meters, which is the vertical height, and t seconds. And then I highlight perhaps the numbers. So 60 meters would be maximum vertical height. Um, the carriage starts at vertical height of 2 meters. That's basically it. Okay. And also we've got this equation here. So they've not actually told us, or not the last question, they gave us all the numbers, the full equation. Here for part A, it says find a complete equation for the model. That's basically saying find all the missing values for A and B to complete that model exactly for H. So in this case, it's actually kind of we kind of have to do the first. Remember when we drew we did this sort of a almost like flowchart thing for modelling or mathematical modelling, where we have a real life problem, then convert it into maths. Well, in this case, we need to find the equation first before we work with it. Unlike the first question where we got given the equation, here we need to work and find the missing bits of to get the equation. Okay, and this is where this data is going to help us. So we're given some information about the roller coaster, and we need to use that to work out A and B. Okay, so what's going on here? That's a roller coaster, right? Well, again, what's this? This is sort of the quadratic, right? So if we it's going to be a negative quadratic because we have negative something of t squared. So negative t squared is going to look like this, which kind of looks like a roller coaster, right? So you start here and then you obviously go up and then you come back down. Okay, so it's like a roller coaster, which makes sense. Okay, so that's what it's going to look like, but we need to work out the values. So what I also notice is that this is in completed square form. And what I also notice is because of that, we are also told about the maximum height. So we've got maximum value, so completing the square is going to help in this case. Okay, so let's go through the data one by one, so the bullet points. So first it tells us, so I'm going to write this down. H is A minus B, lots of T minus 20 squared. It's told us, first of all, that the maximum vertical height, which is h, of a carriage above the ground is 60. So what's going on is, oh, no, never mind. Above the ground, so the vertical height, remember, is how far up you are. So the maximum of the height is 60. So I'm going to call that h max, right, which is 60. But we're not told what time that happens. So again, it's going to resemble this sort of shape, and it's going to be a, the turning point there. But we don't know exactly what time that occurs. But this is where this is going to help us. So we this is the completed square form, right? We know that the maximum value or minimum, but the highest value has to happen when the bracket equals 0, right? Anything to do maximum or minimum means the bracket in the complete square form has to equal 0. That means this whole thing goes away. So this bt minus 20 squared just has to go to 0 when it's maximum. Well, that means then if maximum is 60, well, that means 60 is a minus 0 because the whole everything else is 0. Therefore, we can simply say a 60. And there we are. So then we can update our model because we know what A is. So that's going to be 60 minus B lots of T minus 20 squared. And actually, we know that actually the maximum height, it doesn't ask for this, but the maximum height would then therefore occur when T is 20. Because we know when the bracket's 0, T has to equal 20. So 20 minus 20 gets us 0. Okay, so that's our new model. Now we just need to find B, but we need another piece of information. But they've also told us the carriage starts a circuit at a vertical height of 2 above the ground. So it's talking about when it starts. Well, when it starts, it's when t is 0, right? Because that's the time. So if it starts off in a certain way, nothing's happened yet, so t has to be 0. So and it's told us with t 0, the carriage is a vertical height of 2, so you can say h is 2. But what we can do then is just simply substitute these values into this formula here, because therefore then 2 is going to equal 16 minus b of 0, sorry, minus 20 squared. Well, we can work this out then, because first we have to work with the brackets. So 2 is equal to 60 minus b lots of, and then that'd be 0 minus 20, so that'd be 20 all squared. That'd be 400. There we are. Therefore, I can say that well, and then move 60. So I'm going to solve for b. So move everything else to the other side. So move to 60. So 2 minus 60 minus 58 is equal to minus 400b. Then you can recognise I can just then divide by minus 400. So B is minus 58 over minus 400. And so that will get me uh, 29 over 200. And it doesn't simplify it anymore. You could write it as a decimal. The decimal is just 0.145. That is fine. But I think writing it as fractions whenever you can isn't a bad idea. Anyway, so that's B. So therefore, we've got the whole model. So therefore, H, because now we found all the missing values, H is 60 minus B, which is minus 29 over 200, lots of T minus 20 squared. There we are. Cool, so that's part A done. Then part B says use the model to determine the height of the carriage when T is 40. That's just simply say when T is 40, find H. So T is 40, but then you just substitute that in for H very simply. So H is just then going to be 16 minus 29 over 200, lots of 40 minus 20 all squared. And so then that's going to be uh, 40. We get 2, which makes sense because we got 2 up here to find when we found to find B, the initial what's it called? That's the initial height, the initial when T is 0. But we got minus 20 squared, which would be 400. Well, here I get 20 squared here as well, so I still get 400, so it'd be the same value. But anyway, we get 2, so that would be 2 meters. So therefore, the height when T is 40 is 2 meters. And there we are. So that's that question. And again, hopefully, you see that the whole idea of modelling again. We get some information from real life, right? So we got some values about the heights at various times. Then we can use that to find a model to find the equation to represent the height. And then we can once we found the equation, we could use it to work out some other information like the height at different points of time. So that's the whole idea, right? But yeah, cool. Let's have a look to the next question. Okay, this one. We are given that a company makes a particular type of children's toy. The annual profit made by the company is modelled by this equation here. Where P is the profit measured in thousands, so I'm going to underline that. And X is the selling price in pounds. Okay. There we are. A sketch of P against X is shown in figure 1. So they're actually giving us what the graph looks like. Using the model, part A, explain why £15 is not a sensible selling price for the toy. So again, a fairly common sort of question. You need to use the model to find perhaps when it isn't as reliable as good, right? Um, so to do that, well, we just need to substitute a value in. So 15 is so it's asking why £15 is not a sensible selling price, but as we just underlined, X is the selling price in pounds. Well, X would then be 15 in this case, wouldn't it? So let's try and see what happens when X is 15. Because when X is 15, then P is 100 minus, because we've got given the equation for P here, right? So P is going to be 100 minus 6.25 of X, which will be 15 minus 9 all squared. Simply put that into a calculator. We're going to get 100 minus 6.25 of 15 minus 9 all squared. And we get negative 125. Okay, well, instinct is telling me I got negative. So real life, that probably doesn't make sense. Okay, what does P represent? Well, again, I underlined it. P is the profit measured in pounds, well, thousands of pounds actually. So that's telling you profit would be negative 125, but it's in thousands of pounds, so I need to times by 1,000. which should be negative 125,000, so £125,000. Now, that's a negative. So that's telling you it's a loss, right? Because remember, a profit in a business that can be negative in theory, because that's then telling you you're making a loss. But why would you want to sell why would you want to sell your product if you're going to make a loss and screw your business over? So actually, that is why it's not a sensible selling price. So you'd make a loss of that amount, so 125,000, uh, which is not, which is nonsensical, right? Uh, there we are. Which makes no sense, right? Because why would a business want to do that when the whole idea is to make money and make profit, right? You want to be in the green, not the red. But there we are. So that's fairly common, right? If you see that sort of thing. Oh, if you're given a particular number, why is that model not make sense? Well, just substitute that number in and then see what happens. You probably get a weird that you get a weird number out of it. So here I get a negative, which is not ideal, right? But yeah, so cool. Part A. Part B then says, given the company made an annual profit of more than 80,000. So P, remember the annual profit is P. So it's telling you the annual profit P is more than 80,000. But P is going to be greater than 80,000. But again, P is thousands of pounds. Okay. So we need to then divide that by 1,000, right? Um, to get the value of P to substitute into the model. So then actually P would be greater than 80. Okay. And that's why I underline it. This is why I always underline measurements. They're quite crafty with this sometimes. You might, like we just saw, you might think, oh, just put P's 80,000. But actually, you need to capture the fact it's already in thousands in the model. It's already baked in. So we need to account for that by then scaling down by 1,000 to make that usable for the model. Okay, so that's why underlining the units of everything is important. Okay, so P is greater than 80. Well, we know what P is. P is going to be 100 minus 6.25 of x minus 9 all squared. Because remember, it's asking for the least selling price. Selling price is to do with x, okay? Um, so we need to put that greater than 80. Okay. Now, actually, what this is going to lead to is a quadratic inequality. We have not technically covered that yet. That's in the next section when we look at inequalities. However, that is from GCSE, so nothing actually new should be here. We will look at that again if you need a recap later on in the next chapter. But just as a heads up, this will be a quadratic inequality, but it should be good. Anyway, so then we're going to solve this. Well, let's just expand the brackets first. So we're going to have 100 minus 6.25 of x minus 9, x minus 9. Because remember, if you're squaring it, we're times it by itself. So then we get 100 minus 6.25, well, of x squared. And then take away 9x, take away another 9x, you take away 18x. And then minus 9 times minus 9 is plus 81. And then I'm going to move the 80 to the left. Because like with normal equations, I want to make it equal to 0. So now it's 0 on the other end. So now we can tidy this up. So we're going to 100 minus 6.25 x squared. So I'm going to expand the bracket. Plus, well, it's going to be 18 times 6.25 to expand it. So we're going to get 112.5 x. Then I'm going to do 81 times minus 6.25. So I get minus 506.25. Take away 80 is where the 0. I can then bring everything, simplify, collect all the like terms to get quadratic. So simplify this whole, clear this whole thing up. So I get minus 6.25 x squared plus 102.5x. Then I'm gonna then get all the numbers together. So 100 take away 506.25, take away 80. I get take away 486.25 greater than 0. Okay, now I don't like these numbers. I want to simplify this a little bit, so I'm going to divide by the x squared coefficient. So I'm going to divide by minus 6.25. So that'd be left with x squared, and then 112.5 divided by minus 6.25. I get minus 18x, which is a lot nicer to work with. Then I'm going to have minus 486.25 divided by minus 6.25. I then get plus 77.8. And now that's going to be less than 0 because remember we're divided by negative. So when you divide or times both sides of an inequality by something, by a negative number, you have to flip the sign. So in this case, it's less than 0 now. Okay. There we are. Okay. Well, now this is a quadratic inequality to solve, but you should remember. So remember, you find the critical values by solving the equation as it is equal to 0. So I can do that by quadratic formula. So these will be the critical values, right? So that's going to be x. I'm going to use quadratic formula because I have a nasty decimal. I'm not going to bother to factorize or try to be clever. So x is simply going to be minus of minus 18, so it's just going to be positive 18, plus or minus the square root of minus 18 all squared. That is an 18. Minus 4 lots of 1, lots of 77.8, all over 2 lots of 1. So the critical values would be um, 45 plus or minus 4 root 5 over 5. And as a decimal, because it might be easy to visualize this as a decimal, that's either going to be 10.79 or 7.21, right? To do GP. Why? Because well, it's best to sketch it then, right? Remember, we can sketch quadratic to find an inequality for it. So it's going to resemble something like this. So the y-intercept is 77.8. So I'm just sketching this quadratic, right? Which again, we looked at how to do earlier in the course, in the chapter even. So it's going to be about there, right? 77.8. So 7.21's there, and 10.79 is going to be there. So it's gonna be a positive quadratic because it's a positive coefficient of x squared. So it's gonna look a bit like that, right? Then to find the point, to find where it's less than 0. Wow, that's corresponding to where the whole quadratic. So if y equals the quadratic, right? If y equals this whole expression here, that's saying y has to be less than 0. So it has to be below the y-axis. So here, right? When y is less than 0 or negative. That's going to correspond to when it's under the graph, right? So it's going to be there. So then actually the two values of x is going to be between 7.21 less than x, less than 10.79. Okay, but again, I like exact values, so then I'm going to just write it in terms of this fraction here. So remember, 7.21 would be 45 minus 4 root 5 over 5, less than x, less than 45 add 4 root 5 over 5. So that's, therefore we solved it, right? Okay, so that's sort of the range of values for x. It told us to find the least possible selling price. So what's the minimum value? So really it's going to be this value here, isn't it? It's going to be this 45. So the least selling price is 45 minus 4 root 5 over 5 pounds, right? Uh, but then as a decimal, 'cause, right, that's an awkward number. Remember, that's going to be 7 point, well, it's 7.2111456, da da da. But as in pounds, you're going to want to leave it at 7.21. Uh, Actually, no, because if it was just 7.21, that's saying 7.210. Well, actually, we have 7.211. So this number, this answer here, would actually be less than this number here. But we already said x has to be bigger than this number. So actually, we need to kind of round up. So that's going to be 7.22, isn't it? 7.22 by rounding up. Okay, by rounding up to 2dp. So that's our answer, right? So either to two decimal places, because obviously it's in pounds. You're either going to want it as 7.21 or 7.22, right? Because obviously that's the next digit, that's the next decimal point up. But if it's 7.21, that's 7.210. But that is going to fall outside of this range here for x. Because the absolute minimum value can be is this decimal here, 7.21114. But 7.210 falls less than this number. So it's going to fall outside of the range. So we need to basically round it up to 7.22 instead. So that should be the answer there. Okay, cool. Okay. Then it says, the company wishes to maximize its profits. State, according to the model, the maximum possible annual profit and the selling price for the toy. So I'm going to do it here, part C, part I. So the maximum possible annual profit and the selling price of the toy that maximizes the profit. Well, again, we're going to look at this equation here. So P, I'm going to write it here. P is 100 and minus 6.25 of x minus 9 squared. Well, again, that's just, you should recognize, again, that's in complete square form. So we want to maximize it. We're going to want to make the bracket equal to 0. So the max profit, if the whole bracket is equal to 0, that means it's just simply the 100 at the end, right? So max profit is going to be 100. Is P is 100. However, P is in thousands of pounds again, remember? So to get it in as an actual number, we need to times by 1,000. So that's going to equal £100,000, right? And then the selling price that maximizes it. Well, what x value does that occur? Well, again, if the bracket equals 0, x has to equal 9. Okay, so x is 9, which equals £9 because the selling price is in pounds. And there we are. That's our question then. Cool. There we are. Let's have a look at the next question. Okay, we are given figure 1 is a graph showing the trajectory of a rugby ball. So it's kind of like the first question again, isn't it? We have projection of some sort of object. The height of the ball, I'm going to underline it. So the height of h meters has been plotted against the horizontal distance x, measured from the point when the ball is kicked, which will be here, right? So in this case, we don't have time now. We have x and h. So x is the horizontal distance. How far, obviously, on the ground it's travelled. How far across against how far upwards it goes. Okay, so not necessarily the time this time. Okay, so the ball's travelled in the vertical plane. That's just a fancy way for saying the x-y axis. Okay, so we have an axis of h and x, which kind of is like x and y. Anyway, travel in the vertical plane. The ball reaches a maximum height of 12. So I'm going to underline that, and hits the ground at a point 40 meters from when it was kicked. And then part A is kind of like the other question we looked at. Find a quadratic equation linking h to x. So part A, they're asking us to find the equation this time. So it says find a quadratic equation. So So it's going to look like this, right? H is going to be ax squared and bx plus c. Okay, so it's going to look something like this at the end. Okay. However, it's talking about maximum heights. So actually, we have two choices. We can either use this form here, which is the general quadratic, but remember, we can also express a quadratic as an incompleted square form. Now, when it's talking about maximum height, it's actually best instead that we consider h in complete square form, which remember is going to be some number x plus b, right, all squared, and then we're going to have another number at the end there, okay? Um, and that is the complete square form. And then obviously, if expand this bracket, eventually we'll get back to this form here. So it's the same, right? Also bear in mind the A, B, and C are not necessarily the same A, B, and C here. Actually, I should pick probably different letters to show that they're not exactly the same. So big A x squared and big B x and big C. Okay, so they're not necessarily the same, but hopefully you get sort of the idea. Anyway, so I'm going to use this form particularly because it's talking about maximum height. Now, when you do later on in the course of differentiation, you could alternatively differentiate this, um, and you'd be fine there. But for the purposes of this, at this part of the course, we can recognise maximum height is going to have to deal with completing the square. Okay. And you could complete the square on this, but it's a lot of messy algebra. So it's best to just start here. Anyway, that's enough waffling. So we're going to assume it has this complete square form, which is a general complete square form. I'll highlight that here. Completed square form. Okay. Okay. So now we're going to work the information we're given, and mainly it's we're given a graph, which helps quite a lot actually. So let's look at the information we're given. Well, really, the actual bit of information is this sentence here. The ball reaches a maximum height of 12. That's going to correspond to this turning point here, right? So that's going to be about 12 there, right? And we know it's going to be some value of x then. Actually, so it says a maximum height of 12. And it hits the ground, which is going to correspond to here, because when it hits the ground, then it's not vertically above anymore. There's no vertical height because the ground is at ground level, right? So the ground level is going to again correspond to this axis here. So it hits the ground at a point 40 meters from when it's kicked. So that's when it's kicked. So that has to be 40 then, basically. Um, Okay, but actually, we know that these are the two roots, right? So if this is a root as well, that's just x is 0, isn't it? So we haven't. It crosses the x-axis at 0 and 40, but then actually we can also work out what this number of x is, right? Because isn't that just the middle, midway through? So midway through 0 to something it's the same as this distance here. That's be 20, right? Because half of 40 is 20. And remember, we did briefly talk about it, but we can create a mirror line, and the mirror line is the line of symmetry. That's the line of symmetry is at the turning point. Okay, so the turning point splits the curve in half, right? So if it's so the same distance on the left from 0 to 20 has to be the same distance. So it has to be 20 either side. Okay, so we can work that out. Cool. So now we've got all the information to work out this turning point here, which should be when x is 20 and h is 12. So again, we know that the maximum height, h max, is 20. So, and that occurs again when x is 12. Oh, sorry, no. The maximum height is 12 when x is 20. There we are. Okay, I hope you see that here. X is 20, h is 12, which gives us this turning point there. Okay, so that's the maximum. So again, if we go back to this complete square form, the maximum 12. Well, that's going to be when this whole quadratic equals the whole bracket equals 0, and so 12 is just going to be the number c, isn't it? Um, okay, but also when the bracket equals 0, that means x has to cancel the b out. So that means x plus b has to equal 0 as well. But we know the value of x when it's at the maximum point. It's 20, right? So actually then we can say 20 add b equals 0. So b is negative 20, right? Because when the bracket is set to 0 to give the maximum height of 12, when the bracket's 0, that means x plus b equals 0, which is here. But we know the x value of the point is 20. So therefore we can set 20, add b to 0 to get b's minus 20. Okay, cool. Now we actually found the two values already. We found b and c. Let's then fill that in. So h is going to be a, lots of x, minus 20 all squared, plus 12. Okay. Okay, so that's h. Okay, but we need something to work out the a. But okay, let's think. Let's think a bit more. So the, we worked with the turning point. We can, but the other idea then is to work with the other points that we know. So the other points is this point here and this point there, right? Um, and actually this point here is going to correspond to h is 0, x is 0, isn't it? Because we know initially it's telling us on this graph that there's no vertical height when x is 0 because it's obviously on at the origin, right? Well, that's a point, actually. Alternatively, you could say when x is 40, h would also is 0, because obviously it hits the ground at 40, at x is 40, so therefore if it hit the ground, there's no vertical height, so h would be 0 there as well, which again corresponds to the fact it's on the x axis. Anyway, so actually we've got another point we can put in. So when x is 0, h is 0. But therefore, then, if we substitute that in, 0 is going to be a lots of 0 minus 20 squared at 12. Well, that's an equation for a, right? If I can work out the square number. Well, 0 is, well, that would be minus 20 all squared. That's going to be 400 a. Add 12. Well, therefore, a then is going to be minus 12 over 400, right? If I move the 12 to the other side, then divide by 400, that's going to get me minus 3 over 100. There we are. So that's the value of A. Therefore, I can fill in the information to then get H is, what was the value of H? No, what's the equation here? The equation of H is A, which would work out to be minus 3 over 100. X minus 20 all squared, add 12. Cool. Now actually, we kind of done it there with one only quadratic equation, right, linking H with X. Uh, I guess it depends how pedantic they could be. A quadratic equation, they might want it to look like this form instead, so not the complete square form. But we can quickly do that, right? And it will help in part B because we will need to solve an equation. Actually, no, let's just do it. Let's test our skills. If we expand this out then, so H would be minus 3 over 100 of x squared. So remember, x minus 20 be x minus 20 squared. I'll write that here actually. Plus 12. If I expand this out, I'm going to get x squared minus 20 x minus 20. That would be minus 40x. Uh, add 400 plus 12. Then I can expand this out. So I'm going to get minus 3 over 100x squared. Minus 3 over 100 times by minus 40 is 6 over 5. and then 400 times minus 3 over 100 is going to be minus 12. Add 12. Well, they cancel, right? So I'm just simply left with this, right? And that makes sense because what I wouldn't expect the number to be at the end. There'd be no y-intercept, right? Because the fact it's passing through the origin. Because then the y-intercept is essentially, or the h-intercept is 0, right? So there would be no number at the end. And also we have a negative coefficient on the ax squared, right? It was minus 3 over 100 x squared, right? Well, I have a negative, so that it would make sense of a frowny shape, which is what we got here. So our answer makes sense. Okay, then it says, that's part A done. So that's a very common strategy, by the way. If we they will maybe quite often ask you to find a quadratic equation. If they're talking about maximum height, you could either differentiate if you know how to do that. We will know by the end of year one. We will look at that later on. But we could also use complete square form, okay, in this way. So we talk about maximum height and we need to work out the information. Write it in complete square form. That will allow us to very easily and very quickly find out the values that we need. Anyway, so let's have a look at the next part of the question. The ball passes over the horizontal bar of a set of rugby posts that are perpendicular to the path of the ball. The bar is 3 meters above the ground. Okay, underline the data, the information. Use your equation to find the greatest horizontal distance of the bar from O. What that is essentially saying is a ball. It passes a horizontal bar. So a horizontal is well here, right? But it's saying that it's the bar is 3 meters above the ground. So what essentially is 3 meters above that when his h is going to be 3, isn't it? So if we imagine the line, it'd be a horizontal bar. This would be the horizontal bar, right? So therefore, we need to find the values when the graph reaches 3. H is 3 there, or H will be 3 there. Okay. So I'm gonna get rid of these now. Just to make sure that make the graph clear. We don't need the information anymore. But essentially, these bar the bar we told is 3 meters above the ground. You should be able to recognise and convert that to h, saying h is 3, which should be here. So h is 3 on this axis here. So here or here, right? But to work that out, well, we're going to set h is 3. That's what this means. So if we set h is 3, so that's part B. Where actually, I'm going to do that up here. Actually, there we are. Let's do it here to make room. So part B, H is 3, but we know what H is already in part A, and this is why expanded it actually helped rather than leaving it in complete square form, because now this is a very easy quadratic to solve once I expanded it. So when H is 3, I then get that minus 3 over 100x squared plus 6 over 5x is equal to 3, okay? Because remember that equals h, but h is equal to 3. So now this is a quadratic equation, because if I move 3 onto the other side, I get minus 3 over 100x squared plus 6 over 5x minus 3 equals 0. Okay, I can simplify this because I don't like this really weird coefficient for x squared. So I'm going to divide by minus 3 over 100 to both sides. So I'm left with x squared, then 6 over 5 divided by minus 3 over 100 will get me minus 40 x, and then minus 3 divided by minus 3 over 100 will get me plus 100 equals 0. That's a nice thing to solve. But I'm going to be lazy. I'm going to do it as quite a big number, 100. There's a lot of factors. If we were to factorize or whatever, but to save time, let's just use the formula. So x is going to be, well, minus 40, so that's going to be plus 40, plus or minus the square root of minus 40 squared, minus 4, lots of 1, lots of 100, all over, I don't like this h here, all over 2 lots on. Let me write that book. Clearer. Minus 4 lots of 1, 100 over 2 lots of 1. Then I can put that into the calculator. So then we get okay, we get x is 20 plus or minus 10 root 3. Okay, so as a decimal, that's going to be to make it easy to see, for either 37.32. That's going to be 20. Oh, that's 20 plus 10 root 3, or x is going to equal 2.68 to 2 dp, right? Okay, but in this case we've got two positive values. Did it say to round it to anything? No, it didn't say to round it, so it's best idea to just stick with the surds, right? The exact form. But we've got two positive values for x, so really both of them make sense. But then it says the greatest horizontal distance, so the biggest value of x, right? So if you think about it, it makes sense because this is a positive value. That's going to be the 2.68, right? That we worked out, and this is going to correspond to x is 37.3, right? That we worked out. So those two values make sense, and that makes sense with the graph. But it wants the greatest, so it's going to want this particular point. So the x value is 37.3. So the greatest horizontal distance is this value here, because that's the bigger one out of 2.68. So the greatest horizontal distance, we remember is what x is, and it's going to 20 plus 10 root 3. Oh, which remember corresponds to this value here. Because it didn't say to round it to anything, so if it doesn't say to round it, you have to be a little bit cautious because we might expect you to leave it in third or exact form. Okay, you never know what the mark scheme will be. So you can leave it in this form, and this would be in meters. Okay. So it's roughly 37.3 meters, which is the horizontal distance. Okay. Cool. Then part C says give one limitation. I'll write that part C here. Give one limitation of the model. Okay. Let me get rid of this annotation again. Make the graph a bit. There we are. So give one limitation. So this is where you have to think a bit more in real life and think about exactly actually what could affect the equation or what could affect what's going on. So with limitation. So remember, this is all about throwing a rugby ball in the air. Okay. So in reality, you would expect there to be air resistance, right? And now air resistance is something that's variable, so it affects the ball. It will affect the ball as it goes through the air, but it will affect it differently as the ball moves on. What's happening here? I remember when I talked about earlier, it was symmetrical about the turning point. Is it exactly the first part of the journey? Is it going to be exactly the symmetrical or matching or mirroring the second half exactly? I don't think it is, and that's going to be because stuff like air resistance, right? It's going to affect the motion of the ball differently at different points of the journey, right? For example, some parts of the air might be windier than others, so it will give more air resistance and so forth. So that will be a limitation, and therefore that would affect, for example, the maximum height. Because then, if there was more air resistance, more wind than we expect in the model might not expect there to be any air resistance. Uh, that would actually mean the ball travels less high up, right, as anticipated. So it could result, for example, if there was air resistance that slows the ball down, it might make it move, I don't know, this way or something like that. And you can see the maximum would therefore go down, which makes sense because then its speed is getting converted to kind of oppose the air resistance, so it would be lower. Um, and yeah, that's really it. So we can say the limitation. Uh, the model does not uh, uh, I'm going to say reasonably account for air resistance, and we know that's true because of the fact it's assuming to be perfectly symmetrical, which wouldn't happen because in reality, the ball's motion is not going to be completely like perfect, right? It's going to be slowing down at certain points and then going down at certain points and so on. It would also affect, for example, not just the turning point and what the maximum height, but also when it hits the ground as well. It might make the if it's going slower, it might be less time in the air, so it might end up there, or I guess perhaps it might end up further ahead. But the point is, it can affect what values we get from the model. So it might the values we get, for example, when we found the height to be 3, the values of x, right, the horizontal distance might not be correct. Okay, so it really does affect if we don't account for certain things. It really does affect how valid or accurate the model is. So that's one limitation. Cool. And there we are. Okay, last question now. Pretty similar one, but there are some differences this time. Um, And in this one, we're given the similar sort of thing, but hopefully you recognise this time it's not starting from the origin. Okay, so it's slightly different. Okay, but we're given, it says figure 3 is a graph of the trajectory of the ball after the ball's been hit until it first hits the ground, which should be there. The vertical height, again, I'm going to underline it, h meters of the ball above the ground is plotted against the horizontal distance, x meters. Again, pretty similar. The ball is modelled as a particle. This is very early on in the course. I'm not going to talk about that now, but the ball is modelled as a particle travelling in the vertical plane. Again, that's just saying it goes up, basically, above horizontal ground. Given that the ball, and this is our data, is hit from a point on the top of a platform of vertical height 3 meters above the ground, but that's actually going to correspond to this point there, isn't it? So but initially, when t0, h is 3, it reaches the maximum height, which is going to be this turning point there. Uh, after traveling a horizontal distance of 90, so horizontal distance is 90. So that's going to be that. But it's not told us what this height is, but it's told us it's maximum at 90. And is at a vertical height of 27 after it reaches a distance of 120. So 120 may be there, for instance. So I don't know where, but that's 20. And so that's going to be a height of 27. Okay. It's also given that h is modelled as a quadratic function in terms of x. Find h in terms of x. Well, again, it's the exact same sort of problem as last time. We need to find a equation. Link a quadratic equation. So again, it could either be h is simply ax squared and bx plus c, but it's again talking about maximum height. So that's going to hint we need to complete the square. So actually, instead of doing this, we can just assume we can even instead write it in complete square form of a of x plus b all squared plus c. And essentially, the problem then is to find these a missing values a, b, and c. Okay. So let's work with what we've got. So firstly, let's work with the vertical height because we already have it in complete square form. So it's telling us x is 90. We do not know what height it is, but we know that horizontally it's 90. That means x is 90 at maximum height. Okay, but we do not know what the maximum height is. That's okay, but we know when that has to happen. When the maximum height happens, that means the whole bracket is set to 0. Okay. But that means then if x is 90, then x plus b has to equal 0. but we know that happens when x is 90, so that means 90 at b is 0, therefore b is minus 90. So we can fill that in to then say h is a lots of x minus 90 all squared plus c. So we found b already, cool. We're off to a good start. Okay, it's told us, but then we've looked at the maximum point. Now we need to look at the other points we're given. And it's going to be firstly this point here, right? So this point here, initially when x is 0, h is 3. So we can literally then say x is 0, h is 3. Well, that gives us information to substitute in, right? So when h is 3, so 3 is equal to a lots of x minus 90, but x is 0, so it's going to be 0 minus 90, and that's an a, not a 90. There we are. All squared plus c. We can expand that out, so 3 is going to equal, well, minus 90 squared is going to be 8,100a add c. Okay, that's okay. It doesn't give us anything exactly we can solve. But let's leave it there. Let's look up what else we can get. We can also get, uh, we need another point. Okay, and in general, if we have the amount of missing values we have is how many different points we need, right? So we have 3 missing values, so we need 3 different bits of information or 3 different points. So we worked with 2 points first, and now we can work with the other point. No, the other point is this here, isn't it? Sorry, we don't know anything about this point other than it reaches 0. The height is 0, but we don't know the x value. But this point, we know exactly when x is 120, h is 27, right? So again, we can substitute that point in when x is 120, h is 27. Because remember that comes from the third bullet point here. Vertical height of 27, horizontal distance 120. And that's the whole idea, right? Is to convert the worded information into actual mathematical information. So convert that into what the value of x and h is, which we can use to substitute it in. Anyway, we can substitute that into our model here. So h is 27. That would be a lots of 120 take away 90 all squared plus c. Um, okay, so then I can expand that out. So 27 is going to be a lots of 120 take away 90, that's going to be 30 squared. So 30 squared then is going to be 900 a plus c. Okay, so again, that's not a really, you can't exactly solve it right away, but hopefully you realise that actually these are simultaneous equations. If I label that equation 1 and this equation 2, again, flip back to GCSE how we can solve a simultaneous equation. If I write it down more clearly, say here, 8,100 a plus c equals 3, that's equation 1. 900a plus c equals 27, and that's equation 2. These are simultaneous equations which you can solve for a and c, which I should know how to do from Jesus. So again, we will look at this in the next section. We will look at simultaneous equations, but for now, how can we solve it? Well, let's take, I can get rid of the c by taking the equations away. So if I take the first equation from the second, right, that means 8,100a take away 900a plus c take away c. That's going to be 3 take away 27, right? So then 8,100a take away 900, that's 7,200 a. And then plus c take away c goes away, which is what we wanted. So essentially, we're taking them away. I didn't need to write this, but anyway. So that's 3 take away 27. That's going to be take away 24. Okay, well that is a very nice equation. I can solve for A now, because then A is going to be take away 24 over 7,200. And what does that get me? Minus 1 over 300. Okay, so that's A. Therefore, I can then find C, again by substituting A into either equation. Let's substitute it into the second one, because A, we've got smaller numbers for A. Anyway, so then that means 900 lots of minus 1 of 300 for A, plus C is equal to 27. That's equation 2, remember. Therefore, C, well, I'll just work that out first of all. So 900 take a times by minus 1 over 300 is minus 3, plus C is 27. Hopefully then C, because spot is going to be plus 30. Okay. But therefore we got our values right. We've got A, B, and C. Therefore we can fill in the equation. So H, remember. Oh, whoa, what's going on? H is there, right? So H then is. I'm going to copy that again. So H is A, lots of x minus, what was it, 90? All squared plus C? Yes. But then I can fill in A and C that I just worked out. But that's going to be the same as minus 1 over 300, x minus 90, all squared, plus 30. And again, to make it actually look exactly like a quadratic, I can then expand it to be minus 1 over 300, x minus 90, x minus 90, plus 30. That's going to be minus 1 over 300, x squared, minus 180x, plus 90 squared, which should be 8,100, plus 30. Then if I expand that out, I'm going to get left with minus 1 over 300 x squared. Take times 100 minus 180 by 1 minus 1 over 300. Then I get positive 3 over 5. Then I'm going to do minus 1 over 300 times by 8,100. I then get minus 27 plus 30. That's going to be plus 3. Okay. And that's then going to equal h. And there we are. We've got the quadratic expression for h. Cool. There we are. Then it says, hence find, according to the model, the maximum vertical height of the ball above the ground. So it's talking about the maximum point again. Because we worked out, we know what x value is, but we don't know exactly the height. That's what it's asking now, the height. So the height and the horizontal distance from when it was hit to when it first hits the ground. Let's have a look at part I first of all. Okay, so part I is the maximum vertical height, but that's going to go back to completing the square. Okay, but we don't need to complete the square because we already did it. Right, it's this expression here. We expanded to complete square to get the quadratic form, but we already have the complete square form. So again, I'm going to copy that again. So h is minus 1 over 300, x minus 90 all squared plus 30. Now it told us for the maximum vertical height, which is h max, right? So the maximum height, well, that's going to be when the bracket equals 0 again. But the whole bracket goes 0, I'm just left with 30. So that's your height. So simply h max is 30 meters. And then part II, the second part of the question. It's asking for the oh god, it's asking for the horizontal uh, 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 the horizontal distance travelled by the ball from when it was hit to when it was first hits the ground. So when it hits the ground, it's going to be here, right? And so when it was hit, when it hits the ground, it's going to be basically. this distance here. But anyway, so let's find when it hits the ground before we do anything else. But that hit when it hits the ground is going to be the root, right? It's going to be when it crosses the x-axis. Well, that's going to be when the quadratic equals 0, isn't it? We've worked out what the quadratic is, so this whole thing has to equal 0. So minus 1 over 300 x squared plus 3 over 5x plus 3 equals 0. So now I'm essentially solving that. So again, I'm going to divide by minus 1 over 300 to make it nice to work with. So I'm going to get x squared, then 3 over 5 divided by minus 1 over 300 will be minus 180 x. And then 3 divided by minus 1 over 300 is minus 900 equals 0. Okay, so a lot nicer to work with without the nasty fractions. Well, then I'm going to use quadratic formula. So x is going to be plus 180 because minus 180 plus or minus the square root of b squared, that'd be minus 180 all squared, minus 4 lots of 1 minus 900 over 2 lots of 1, and therefore if I solve that, put that in the calculator, uh, I get 1, I get this value is x is 184.8. I'm going to do 87 or minus 87 meters to 2 dp. Again, I've got two solutions, but this time round, one of them is negative, but x is horizontal distance, and distance is a positive number, right? So it has to be positive. So x has to be at least 0. So we have to reject this solution, right? So simply x is only 184.87. Okay, so that's going to correspond to obviously this point here, 187.4. That's circled there. But it's then asked for the horizontal distance travelled by the ball. So there's horizontally how far along from when it was first hit, when x is 0 to here. Well, that's just going to be the number here, the 187.4. Okay. Then it says to the nearest meter. So x is in meters. So if it's in meters, it needs to be to a whole number. Okay. So I need to get that decimal to the nearest whole number. And that's going to be 185, right, meters to whole number, or the nearest meter, I'll just say. And there we are. Cool. Then for the last question, the possible effects of wind or air resistance are two limitations. So we discussed that last time. Give one other limitation to the model. Okay. So I'm going to do that up here. So, we discuss how air resistance affects it for the fact that it's assuming to be perfectly symmetrical around the turning point, and that it won't slow the ball down or anything like that. But they've already told we can't use that, so we need to come up with something else. So these are sort of stock answers. They do love asking this. So when you get used to these sort of questions, you will start to immediately remember certain limitations that you can just apply. Air resistance is one of them, but they've already given that. Well, the other thing, um, I did speak briefly about being a particle. I'm not going to talk about that now here, but that would be a limitation. When you look at mechanics, we do look a lot about stuff like this, about things called particles. You won't if you just start the course, because this is that start the course. I'm not going to expect you to be familiar with that. But another limitation, a cool one which applies, is the fact that actually, well, think about it, x is a horizontal distance, so it's exactly on the floor. Now, think about it in real life. Is the floor exactly going to be perfectly 100% flat? It's nice. It's going to be slightly bumpy or hilly at times. That will affect the answer because potentially, if it's hilly around the end point, it's going to affect actually the point where, well, first it's going to affect the point where the value of x, the initial distance of where you throw it. Because say, for example, it could be like a little hill, so it could be like throwing it here, and then there's a little hill, and the floor is there, right? Rather than being perfectly flat like this. So if so it could affect basically where the ball hits the ground. It might not be 187.4 if the floor, the horizontal floor, the distance was perfectly flat. That's not real. That's not reality. Ground is not perfectly flat. So in reality, so a limitation is simply is the is what is it the horizontal distance or the horizontal ground will not be perfectly uh, flat or horizontal, right? And that's your limitation because the model assumes it is. Okay, in order to get this flat like x-axis, right? But again, if it wasn't, it would again affect how high up you are. Not sorry. Well, if it's hilly, then it might affect how high up you are. So if it's a bit hilly, it might actually affect the vertical height because it might be higher than anticipated. If, say, you're standing on a little hill at the start, well, it might not be 3 meters you're up against, but the hill gives you some extra inches, right? So it might you might actually be starting higher. And again, if the ground is a bit hilly at this point here, again, the actual ground level might actually be here if it's a bit high up. So that will affect actually the value of x where it hits the ground. So that will affect how accurate the answers are. But yeah, that's another limitation. So yeah, I do love asking these sort of questions. So it's good to have these ideas in the bank. Um, the idea of air resistance, the idea of the fact the ground is not perfectly flat and stuff like that. So yeah, so there we are. So that is essentially a good bunch of questions relating to modeling quadratics. Hopefully, you see the idea of modeling now. The whole idea that we try to find some equation, in this case, quadratic equation, to given some information or data about the, the, the scenario. Then we can make an equation. Therefore, we can use the equation to solve some stuff like finding the maximum height, solving when it hits the ground, so the solutions to the quadratic, which will then tell us stuff about what's going on. Okay, and yeah, and that's another common thing again. They might ask you to find the function, which again you need to follow this sort of procedure. Okay, which we've done here. Okay, cool. So that's it for this chapter. But yeah, I'm going to leave that there.